The actual process, computational process by which we do combustion analysis is most easily described using the diagram method. So we're starting off with a compound which is CXHYOZ. We're adding O2 to it, and we're going to determine by measuring the weight gain of the calcium oxide to calcium carbonate and the magnesium sulfate to magnesium sulfate hydrate. By that weight gain, we are going to determine the number of grams of CO2 plus H2O. And this is one problem which does not obey the general rule that I gave you for the diagram method in the last class. Is this reaction, as I've written it, balanced or unbalanced? Put it in chat, please. Yeah, the reaction's unbalanced. And it turns out for the combustion analysis process, for the computation, you don't need to balance the reaction. So I guess the rule is when you're using the diagram method for anything but combustion analysis, probably balance. For combustion analysis, in the standard way, you don't need to balance, but I do have to warn you, I could write you a combustion problem where you will want to balance, and you're just going to have to keep an eye for it. But certainly in the standard combustion analysis problem, we don't balance. And as I told you, we're going to measure the weight gain. And we measure the weight gain, and I'm just writing this down. These are the weight gains we find. It was 54.423 grams of CO2 produced, and 12.380 grams of H2O. These are what we determined experimentally. And we also weighed the starting compound. This will be important because this will get us, it turns out, the amount of oxygen. 25.03 grams of the original compound, the unknown compound. Which is, in fact, a pure compound. It's just one compound. Okay, that's the data. So just like before, we put the data. And now, what would you like to do with the grams of CO2 and H2O? What did we do last time? Put it in chat. Yeah, we love turning things into moles. And to turn it into moles, we're going to need the molecular mass. The molecular mass of CO2 is 44.01 grams per mole. And the molecular mass of H2O is 18.02 grams per mole. And if we convert that, we're going to find out we have, and notice that all these numbers are to how many sig figs. And lots of sig figs is definitely the way you want to do on combustion analysis. How many sig figs are all these numbers? Yes, they're all to 5 sig figs. And so remember that I like in the intermediate steps sometimes to go to even more sig figs, but certainly don't go to fewer or you're going to have a hard time with this problem. So 6 sig figs certainly is going to be enough. Moles of CO2 and 0.687014 moles of H2O. And why did I want to get, do you remember why I wanted to get the moles of CO2? What was it? What did I say in the last clip? What was the point of getting the moles of CO2 and the moles of H2O? Exactly, we want to know the number of moles of C and the moles of H because that's giving us a big clue on the initial compound. And so the ratio of moles of carbon to moles of CO2 is the same because there's just one carbon in it. So there's exactly 1.23661 moles of carbon inside 1.23661 moles of CO2. But for H2O, what is the ratio of moles of H2O versus moles of hydrogen atoms? Put that in chat, please. Put it in chat. Exactly, it is 2 to 1. So I'm going to take this number and multiply by 2, and I now 1.37403 moles of H. Good, so now I know the number of moles of carbon and moles of H, and which element do I not yet know the number of moles of? Put it in chat. It's the O, and so we need to figure out how many moles of O, and the way to do that is that we know the number of grams of CXHYOZ. So let's subtract off the number of grams of carbon and the number of grams of hydrogen. And the way to do that then is we have the moles of C, we want the grams of C, we use the, what's it called again? Put it in chat. It's not the molecular mass, it is the atomic mass. It's 12.01 grams per mole for carbon. But these are things, and for hydrogen it's 1.01 grams per mole. It looks close to 1, but you know, we're doing to like 5 or 6 figs, so you really want to write this down correctly. And this is 14.8516 grams of carbon. Grams of carbon, and 1.38777 grams of hydrogen. And so we are going to subtract those two number of grams. We'll subtract the 14.8516 grams. We'll subtract the 1.38777 grams. That's the amount of grams of carbon and hydrogen, and that will give us the number of grams of oxygen, which is 8.79363 grams of oxygen. And we want the number of moles of oxygen. Its atomic mass is 16 grams per mole, and that is 0.54960 moles of O. And so we now know that we have the three number of moles of our three elements. We're well on our way to finding the stoichiometry. And we know that it's carbon, we've got 1.23661 moles. Hydrogen, we've got 1.37403 moles. Oxygen, we will have 0.54960 moles. And that doesn't really look like a chemical formula yet, because chemical formulas are in whole numbers. And so the trick to do is take the smallest of these numbers, which is the 0.54960, and divide each of these by it. This is the process to turn it into whole numbers. And when you do that, and keep the places, it's carbon 2.22500, hydrogen 2.5000, oxygen 1.0000, and they're almost now whole numbers. What do I have to multiply these three numbers by to make them whole? 2.25. What do I have to multiply to make it whole? Put it in chat. Yeah, I have to multiply them by 4, because this is C 9/4. This is H 5/2. O1. I multiply all the elements by 4. I get C9 H10 O4. And this is called the empirical formula. There are two types of chemical formulas, and let me just explain what the two types are. I'll use benzene. Benzene is C6H6, and that's called the molecular formula. The benzene molecule really has 6 carbons. I have to draw the bonds. I can't help it. And 6 hydrogens. That's the molecular formula. But the empirical formula is just the ratio. It's the stoichiometry of the elements to each other. And so the empirical formula for benzene is just CH. We've removed all common factors.